I will thank Professor Soler for having me here. And yeah, so I'm going to talk about some work we have been doing in collaboration with Jérôme Dubail and Yanis Brun. But on the way, we'll also mention some work with my supervisor Pasquale Calabrese and a student of us, which is Sara Murciano. Okay, so this is the outline of the talk. So in the first part, I'm gonna give you some info, which are the main insights allowing to use conformal field theory to deal with the inhomogeneous system. And in the second part, instead, it's a step towards the idea of using the same tools to go to deal with out-of-equilibrium system. And in particular, I will show that this tool, in fact, allows you to compute the dynamical correlation, for example, in the breathing Tonks-Girardeau gas. And the new result I'm going to present has to do mainly with the one-particle density matrix and the fermionic propagator. Okay, so I'll start very simple, in particular for this audience. And so yeah, just by reminding why conformal field theory has been so powerful it's so powerful to describe low-dimensional, in particular 1 + 1 dimensional critical systems. And so if you consider a generic system with very broad assumption, like you ask for a local interaction, you ask that, I mean, at a certain scale, you can look the system as being a Poincaré invariant. Then if for some reason your system also has symmetry, scale symmetry, meaning symmetry under global dilatation, then in general what happens is that it is automatically invariant under a larger class of transformation, which are the conformal transformation. And roughly speaking, these are nothing but transformation which stretch the coordinates while leaving the angles unchanged. And in particular, in 1 + 1 dimensional conformal field theory, this group is infinite dimensional, and this allows in many cases for exact calculations. And the point is that this is exactly the same of one-dimensional critical system. So in particular, these are special points in the phase diagram where basically the correlation length of your system diverge. Therefore, you don't have any scale in your system, which becomes scale invariant, and a fortiori, as we said, conformal invariant. And for this reason, conformal field theory has been extremely successful to describe such systems. And in particular, among others, it gave many insight about the physics of out-of-equilibrium, in particular in the specific evolution given by, the simple evolution given by the so-called quantum quench protocol, which is nothing but basically the evolution after a change in some parameter in your Hamiltonian. And also, it gave universal prediction about entanglement. And in particular, entanglement, it's a quite a complicated quantity to compute in the macroscopic models. Instead, from the conformal field theory point of view, so this task basically boils down to compute, to solve elementary exercise on these Riemann surfaces. So on quite a bit complicated geometry, but still is way easier than going to the macroscopic model. But so there is a caveat, meaning that so conformal field theory in general does not allow you to take into account the strong variation of energy in your system. So mainly described like excitation around the given energy, and so meaning that it doesn't allow you to take into account strong variation in the scale of your system. And this caveat is actually important, because in all experimental setting we deal with inhomogeneous systems, and so this seems at least a priori to rule down the possibility to deal with such a system with the conformal field theory. for example, if you think about gas in experiment, they always lie in trapping potential, and therefore they come with an uniform density. And this is also the case for many out of equilibrium situations where, as for example, trap release. Also in this case, our system is described by uniform density. And so the question is, do we really lose everything, or we may still recover a CFT description for such in some situation and under some assumptions, of course. And in order to answer this question, we will focus on a gas of bosons. So these psi are the bosonic variables, and this G is the interacting strength. And in particular, we will focus on the limit where G goes to infinite, which is also known as the Tonks-Girardeau limit. And in this limit, the model is known to be mapped to a free fermionic model, where C now are fermionic variables. Okay, so we start simple by a uniform case, meaning the potential, we put the potential to be equal 0. So in this case, so the propagator, since we are in the uniform case, it can be written in terms of the Fourier transform. And if we linearize around around the extreme of this integral, which are the Fermi points plus or minus kf, this is what we get. And a crucial point is that now these two terms can be interpreted as the right and left component of a Dirac field, and this ultimately allows to find out the underlying field theory described in this model, which is nothing but the massless Dirac Fermi in two-dimensional Euclidean spacetime. So now, what if now we switch on a trapping potential? Again, we want to understand if there is an underlying field theory, and in order to define such theory, so first of all, we will rely on the so-called local density approximation, meaning the main assumption of this approximation is that is for the system to exhibit a separation of scales. In particular, we will assume the existence of a mesoscopic scale L, which is much smaller than a macroscopic scale, say, for example, the dimension of a trap, so that at that scale the system can be seen locally as homogeneous, but still much larger than a microscopic scale, which can be given, for example, by the interparticle distance, such that still at this scale L we can have a thermodynamic number of particles. And so the point is that this approximation becomes exact in the semiclassical limit, and therefore since the thermodynamic limit meaning the limit where the number of particles is very, very large, since this thermodynamic limit is a special way of taking the semiclassical limit, if you want, then in this limit our results are expected to hold automatically. Okay, so we start simple with the specific trap, which is the harmonic trap. So in this case, we know the profile of so basically the density profile is known exactly and is given by the Wigner semicircle law, which is this is the form of our density. And so again, what we are saying is that so if we go to a certain value of x, we can see the system as locally homogeneous, and therefore we can define a local Fermi energy, a local Fermi momentum, and for the same reason, we know that at this scale we want the propagator to have the same form as in the uniform case. So now the question is, does it exist a theory a global theory globally defined such that locally it looks like the uniform one? And the answer is yes. And it's nothing but a massless Dirac fermion in two-dimensional space-time, but this time this is curved. So the idea is the following: if you write in general the propagator for such theory, this is the form that you get. And if you ask for this propagator to match with the one that locally we know we want for our theory, this defines for you the coordinate z of your theory here, which now lives on a strip basically, and also your curve metric. In particular, in such coordinates, as we call isothermal coordinates, the metric takes this simple form. So basically, it's the flat metric times a conformal factor, and this conformal factor is exactly fixed by the Fermi velocity. So the idea is that so basically we have this our density, which is now space dependent, and it's exactly this space dependence which fixes the underlying curved metric.
But you don't need a harmonic trap to do that.
No, I don't.
E of x would work, right?
Exactly. Yeah, that's what's coming now. So exactly, because now the point is that we did that. We started with the harmonic trap, but actually, since we are in the semi-classical limit, we don't need to know exactly now the shape of the of our density, because we are in the semi-classical limit. So the we can use the Bohr-Sommerfeld quantization rule in order to define for generic potential a Fermi momentum.
VF is KF?
Yeah, VF is KF. Yeah, exactly. Yeah, I'm using. I mean, it's the same. We are. We are in the conformal limit. So yeah. And therefore, now that we have defined this Fermi momentum for each potential, then we have automatically the underlying field theory for any potential. And again, this is nothing but a massless Dirac fermion in two-dimensional curved space-time, where in general now the coordinates take this form, and so this coordinate in general will live again on a strip whose width is generally fixed by the potential and the chemical potential. And what is nice here is that this coordinate has actually a nice interpretation as the time travel of a particle in this curved space. And again, the metric instead is fixed exactly as before. Okay, so this is just the summary of this curved space CFT approach in a nutshell. So the idea, as we said, is that we have an inhomogeneous system in a flat space, and what we are saying is that this is basically equivalently described by a uniform system, but on a curved space, where now the inhomogeneity is basically encoded into the metric, okay, into the conformal factor of the metric.
So in your case, the inhomogeneities are only along the x direction, so everything is flat in the y direction.
Yes, for now, yes. So in fact, now this is the first part, which is about equilibrium. Then exactly what we are trying to do with the Jerome is trying to go also, considering also the inhomogeneity in the time direction. Okay, so now the question is, of course, how the calculation really actually work, because why is that useful in calculation? So the idea is that we want to consider, so the object we are interested in are something like that, which are in general correlation functions, which now are computed on this curved background. And the point is that if we consider a Weyl transformation, which now we see it as not a transformation on the coordinates, but on the metric itself, so that it really changes the space, going from the curved space to the flat space. So the point is that under this transformation, primary fields of conformal field theory just transform with the conformal factor being here delta, the dimension of the field, and therefore up to some conformal factor we end up to computing the same object but in flat space. and that we know how to do. It's just a standard conformal field theory. So this is the idea. And so this method has been applied already in a couple of works. In particular, so in this work, Jérôme Dubai and his student Yannis Brun considered the one-particle density matrix, which actually is quite difficult to obtain directly for the macroscopic model, and they were able to obtain asymptotic expression for arbitrary external potential. This is the case, I guess, for the harmonic trap, but they also have results for other traps. And another reason why this method is quite powerful is because it allows also for the calculation of entanglement entropy. This, for example, is there is some result for the ground state entanglement entropy. And for example, what I'm showing here is for the case of a double well potential, and actually, so recently we together with Pasquale and Sara Murciano, we extended these results also to low-lying excited states of conformal field theory. So the idea is that once we are in conformal field theory, the low-lying excitation are the ones created by applying a primary operator to the vacuum, at least in unitary CFTs. And what we consider is basically the excess of entropy with respect to the ground state, and also in this case we were able to give prediction. So this is for the vertex operator. Here we were considering bosonic field theory. So this is the excitation created by the vertex operator, which basically does not change the entanglement at all with respect to the ground state. And this is the derivative operator. Okay.
So this was all for the free theory.
Yeah, that was for the free field.
What would happen with interactions? Does this carry through, obviously? Or?
So that's a good question. There's something that we would like to. So there's one of the things that we would like to investigate soon. So the problem, there are problems, of course, in a sense. So I would say that. So, for example, there is this work by Jérôme and Yannis Brun, where they consider finite interaction, okay? And so the first problem is the following: that if you, for example, consider a Latinger liquid theory where now the constant depend on space, this will break conformal invariance because you end up in a theory. So let's say if you have something like that. You have something like that. So and this would be conformal invariant, but then this break. So at least from this perspective, it doesn't seem very straightforward. But I will mention something that goes in this direction, in particular for out of equilibrium at the very end of the talk. Right. I mean, then you can, if you want, you can consider cases where the theory is interacting, but this still doesn't depend on space. So there are particular cases, even interacting, where you can use this stuff. But there is some issues.
Sorry.
Yeah, no problem.
If you took the initial physical model of fermions on the line and added a 4 fermion interaction and a harmonic trap, would that be described by the model you wrote? Some other model?
Yes.
Okay.
Yeah, it would. Yeah, because the idea is, so the way you get this is basically you say that, so in this semi-classical approximation, your model is basically, so the degrees of freedom you want to keep track of are the ones, so you define a density. You write this density as rho 0 times the derivative of a given Gaussian field, and this is something like phi plus. That's how you do derive this. It's an approximation, of course, but. Okay, so so the main focus of this talk is what about out of equilibrium situation? Can we still use some tools of those that I just described? And again, in order to investigate that, we are going to consider the Tonks-Girardeau gas, and in particular what I call breathing Tonks-Girardeau gas, which will be clear in a while. So I will consider a time-dependent potential, in particular the following protocol, which is given as follows. So the initial state is the ground state of in a trap with a given frequency omega 0, and I let it evolve with a space-time dependent potential, but still harmonic for now. But can be whatever. I mean, whatever but harmonic. So W of t, if you want, is a generic function of time. And so the idea is that now there is an important point to make. That is the following. So if you want, at least for what we saw at equilibrium, the density profile was, in a certain sense an input of this method. Okay, so we need to have this classical background, and then on top of that we construct our quantum fluctuation via CFT. Here the idea is that now in the dynamical situation, the equivalent, if you want, of the local density approximation is hydrodynamics. So now our background will be fixed by standard hydrodynamics, and which is just these two equations. Basically, this is the continuity equation. This is the conservation of momentum, where here this is the pressure of the gas and this is the potential, and the pressure of the gas is just a function for this, in this case, of rho, which is something like rho cube. Therefore, this is a closed, if you want, it's a closed system for rho and u, where u is the hydrodynamic velocity. And the point is that for generic harmonic potential, this system can be solved exactly in terms of this parameter b of t, okay, which is called a scaling parameter, something quite known in the community of cold atoms, and it is given by the solution of the Ermakov equation. Okay, so now, of course, we could consider generic, at least harmonic evolution, but we will focus, at least for giving explicit result, to a particular particular evolution protocol, which is the quench, the frequency quench. Basically, we will start in the ground state with a certain frequency omega 0, and at time 0 we will quench the frequency of the trap to a different frequency omega 1. And the reason for the main reason to focusing on this quench is that in this case the Ermakov equation can be solved explicitly, exactly, and we have an analytic solution for this parameter b of t. And for example, this is how the density as a function of x and t looks like. So that's why. So from here it's clear why we call this breathing mode. Okay. So the goal now is to compute dynamical correlators at different times, so it's object of this kind. And as I said already, there are two main ingredients here, which is on one side the hydrodynamic solution, which gives the classical background, and is also the one which will fix, as we are going to see, the metric. And on top of that, we want to construct quantum fluctuations via CFT. Okay, so it's easy to see that in this case, the underlying metric has this form, where basically the hydrodynamic velocity just gives a Galilean boost. Okay, it's just like in these coordinates we are following the hydrodynamic evolution. And then on top of that, we have a Fermi velocity. So to understand this, the simplest way to understand this is by looking to the null geodesics, which gives particle right and left movers, which moves with a velocity plus or minus Vf on top of the Fermi velocity, which is exactly consistent with what we saw from the other dynamic picture. Sorry. And now the idea is that since we are in CFT, so everything is ballistic basically, and therefore, if, for example, if we were in flat space and consider like two generic operators, two generic points in space-time, let's say that they are a chiral operator, for example. And so basically, what you can do is that since you are in CFT, you can easily trace them back along their trajectories in time, and therefore, what you can say is that the correlation between these 2 points is nothing but the correlation between the same points traced back at time equals 0. And so now the idea is the same because we are against CFT. The only difference is that now our geodesics are curved, so we have to trace them back along their curved geodesics. But the main insight of this slide is that basically once we trace the operator back in time, we are back to correlation function at equilibrium that we know how to compute with the technology I just introduced before. So that's the idea. I mean, of course, if you want, you could also, for generic case, you could also find isothermal coordinates which depend on space and time, but this is in general way more complicated. So here the idea is that you just need to trace them back, and in some cases it's easier. Okay, so in particular, for the harmonic evolution, we are going to see that this tracing back procedure is very easy, and this can be understood with what we like to call a kind of a holographic picture, but it's just words, okay, for now. And yeah, so the idea is the following: if you look in this plane, x and t plane, so basically what we have is that we have our particles which are moving along their geodesics, and they are bouncing at the boundary of this breathing system, and they basically live in this strip, which is with the curved boundaries. Now the point is that you can describe the very same motion through as the projection in the x and t plane of a circular motion taking place in the xy plane, in the xy plane where now y is just a fictitious coordinates I introduced, and now the point is that in this circular motion, basically we can describe those particles through an angular variable, and of course, since as you see if you think to this as a circular motion, then the radius of this motion is basically changing in time. Therefore, the energy of this problem is not conserved, but the angular momentum is. So basically, we can define an angular velocity, and once we have that, basically we have a very simple way to trace in these angular coordinates the trajectory back. And so using these new coordinates, basically this is what we get at the end. So every operator will be traced back with the same angular velocity, and therefore we go back, as we said, to an equilibrium correlation function. Okay, so now I'm going to show that basically this can be applied straightforwardly to obtain the one-particle density matrix that, as I said at the beginning, is instead quite demanding to be computed directly in the macroscopic model. And so actually, I mean, for this particular quantity, it's better, as I was mentioning before, I did everything in the fermionic variables, but you can do basically the same with bosons. And so the equivalent theory, so if you want the bosonic counterpart of the massless Dirac fermion is nothing but a Gaussian free field, bosonic free field, which is defined in this way, where H is the bosonic field, and it divides just in this way in the chiral and anti-chiral component. And in this theory, you can basically write your one particle density matrix in terms of the operator of the theory, which is the thing that you do always. You have a macroscopic model, you have some fields, and you want to write them in the in terms of the fields of the theory, and this is nothing but basically a vertex operator in this theory. And therefore, what you do at the very end, you have to do with the simple correlation function of vertex operator with the theta and theta prime at different times. Then you trace, you basically trace this angle back as we saw for generic operators, and this is what you get. So basically, what I'm showing here is again for the particular case of the quench from omega 0 to omega 1, and so here you see again this boundary corresponding to this breathing mode. But probably, so the most striking feature of this plot is the following. So is the appearance of these curved light cones, which was already observed actually in a previous work by Jérôme, Jean-Marie, and Pasquale. So basically, this is what you would expect in flat space, right? So what you are doing here. So now, actually, to be more precise, here I wrote two generic times, but here what I'm showing is okay. So I fixed basically this point to be 0, 0. And so what are...
sorry, the colors are this value.
The what?
I don't understand the color, the color value.
Yes?
You have X, T, and the colors are the values of this density.
Yes, yeah, exactly, yeah. Yeah, so this is 0, so outside is 0 because you have the boundaries. Inside here, it's we are around these values here, and then you have these peaks, basically. Okay, so basically this is what you would expect in flat space, because basically what you are doing is that you are creating a small perturbation at a given point in space-time, and from there you expect some light cone to spread at a given velocity, which is usually the Fermi velocity. Now, this is exactly the same, so the origin of these light cones is exactly the same, but now our velocity, as we saw, will depend on x and actually also time. I forgot here. Also time, and that's why we see some curved light cone.
But why doesn't the big spot is at t equals 0?
Right. Should be. Yeah. No. So probably yes. You're right. Yeah. I consider actually a different time. So I should be something like should be something like that. I chose this one because otherwise, the light cone goes something like that. Okay, was clearer like this. Okay, and right. Okay, so as you probably saw here, I have no numerical check for that because in this case, as I was saying, it's a little bit hard to go and have the and calculate this quantity in the macroscopic model. But for that, we instead have the numerical check for the fermionic propagator. So in principle, here you can play the same game, okay? And however, we are going to see that there is a small something else to be taken into account. And to understand better, we go for a moment back to the uniform case, where we saw already that this is the form of the propagator. And the point is that, so as you see here, this is what I wrote at the very beginning. But if you look carefully, basically, in the saddle point approximation, you have two regimes. Basically, there is a regime where you have, where you have a point inside which will give the main contribution, okay, to the saddle point approximation, and in this case, the contribution from the stream instead will give just the next to leading corrections. And then instead, if there is no saddle point inside, then the main contribution will come exactly from the extremes. So these two regimes are nothing but basically the outside and inside light cone regimes, which in the flat space are just defined by this equality here. And so if you look to the outside light cone regime, as we said, there is no stationary point inside, and therefore the main contribution comes from the extreme, and this is the shape of the propagator, and this is equivalent to say that we can write actually C and C dagger as a combination of right and left movers in order to obtain this form. And as you see, they actually, these two guys come actually with a phase, which is nothing but the WKB phase, okay? So the semi-classical phase. And instead, if we go in the regime inside the light cone, there will be the leading contribution, which comes from the stationary point, and this is this form. So basically, there is an amplitude and there is a phase. So this again can be easily understood from semi-classical. From a semi-classical approach. So basically, the idea is the following. So we are in the ground state of free fermions, and if you go to the phase space, so basically the Wigner function of such states is nothing but a strip. Okay. So basically, this is 1 inside and 0 outside. So it's 1 for every k between minus kf and kf, and this is 0 outside. So the point is that this propagator is related to the probability of destroying a particle at time t equals 0 at x equals 0, which in this language would be is equivalent to basically destroy a slice at x equals 0, and to create a new one at a new position x at time t. So as time passes, basically this slice now evolves. So each particle evolves with its own momentum, and this is the new x position where we want to create a particle. So basically, this probability is related to this area here, which is the intersection between these two slices, and. So in general, what we expect for this term is the area of this red region to appear here, which in this case can be shown to decrease as 1 over t. And instead, the phase is nothing but the phase of a single particle in Lagrangian formalism. So also in this case, we know in principle how to generalize also to inhomogeneous situation. Of course, this has to be done case by case. Okay, so now we go again to the harmonic time-dependent trap, and so we saw that also in this case we have this phenomenon of this curved light cone. So we will expect two different regimes, which is the one inside and one outside the light cones. And if you start with the outside light cone regime, so the point is that also in this case you, in principle. The point is that you also here you can write your fermionic variables as a sum of two chiral fermionic variables, which are now associated to the new Fermi points, which are the ones we saw before, given by the hydrodynamic velocity plus or minus the Fermi velocity. And also in this case, they will come with a phase. Not unexpectedly, this is nothing but the WKB phase, which generalized like this. So basically, it's again given by the integral of this momentum plus this function that you just require. You find by requiring consistency with the local form of the WKB phase, which should go back to the uniform case. I mean, this is just algebra, but the idea is that this is nothing but the WKB phase. And yes, so this is what we see. So basically, in this case, this is the numeric, so the exact propagator computed in the model, in the free fermions model, and this is instead what we obtain from CFT. So basically, we see that in fact, as we expect, we have these two different regimes, okay, and CFT, in fact, is expected to give the main contribution outside the light cone. So, for example, if you focus here on a particular time, which is here it's the alpha period, where we are exactly for every x we are outside the light cone, we see that basically the comparison between the CFT result and the exact is perfect. But but instead we are missing. We already see here that we are missing something inside that we know what it is now. So in fact, if we go inside now, we expect this to be the leading term, which is the generalization of what we saw before. So in particular, for the case of the quench, this can be computed easily again by looking at the Wigner function. So at time 0 in these rescaled variables, the Wigner function is an ellipse basically, and again we have to look to the correlation. The correlator we are computing is related to the probability of destroying a particle t equals 0 at x equals 0 and creating a new one at another point. And now what happens is that in time, if you consider the quench from the quench protocol from a given frequency to another, what happens is that this ellipse just starts rotating, and so we can easily again computing this area here, which in this case is given by this function. So and this generalizes this part here basically, and this is again instead the particle in the Lagrangian formalism. Okay, so now we can also look to what happens inside, and again you see if you focus on this particular value of time where you are exactly for all x which are where the function is non-zero, you are always inside the light cone. You see again that the agreement is perfect. Now, if you move a little bit up, you start seeing some effect, because I mean the only point where this formula is not expected to hold is where you are close to the light cone, okay? Because I mean also from the saddle point approximation you already see that this is not is the only point where the saddle point approximation does not hold even for the uniform case. And in this case, you see that the closest you go to the light cone, you start seeing some deviation. And this can actually also be related to the fact that in this case, the two Fermi points are very close. And so actually, I was discussing with people doing semi-classics in LPTMS, and they were saying that this is also something known in semi-classical world to appear. And right, so this is more or less where we are now, and there are actually some two main directions where we want to generalize this kind of stuff. So the first one is what about multi-Fermi points? So as I was saying, I was always considering this harmonic evolution, and I was starting even in the ground state of an harmonic trap, and therefore I was in the case where all the time I still had just two Fermi points. Instead, in general, for example, the easiest case you could consider is the quench from a double well, for example, and in this case, even if you look to an harmonic evolution, you will see that you will have, something like the Wigner function will be something like that. And so even if you consider an harmonic evolution, as time passes, this starts rotating, and therefore at a given point you start to have 4 Fermi points. So a generalization would be in this direction, but we expect also in this case all this structure to hold. Of course, instead, way more difficult is to try to understand if this method can say something about some thermalization issues, and for this I mean the following. So, as I was mentioning, as far as you consider an harmonic evolution, basically you can have, yes, the situation where you have more than 2 Fermi points, but what happens during the evolution is just that your Wigner function just starts rotating, basically. So you at most will have a finite number of Fermi points. Instead, if you consider an anharmonic evolution, this is what you get, basically. So you start, the Wigner function starts creating this kind of spiral, and so you have more and more Fermi points, and yeah, so I don't know if this method can say something about this kind of problems. But probably the most interesting direction to be considered, as Professor Staller was also asking at the beginning, is what about interactions? And we have some idea of how to deal with, in particular, especially with the simple with specific situation. So, of course, if you consider a generic interacting model, I mean, this is very messy. But instead, in particular, the way I presented this kind of approach seems to be quite suitable for a generalization to integrable models. So basically, recently there has been a lot of work in what is called the generalized hydrodynamics. So basically, there were these works where so basically we know, at least for those models, consider for a special class of models which are called integrable, how to write, which are interacting. We know how to write the hydrodynamics also for those models. And in this approach, basically the idea would be to use, instead of standard hydrodynamics, to use this generalized hydrodynamics and then construct again as the classical background, and construct up on top of that the quantum fluctuation using conformal field theory. But this is still a work in progress, actually at its very beginning. So yeah, I will thank you for the attention. Yeah.
I got a bit confused, I admit, about the inside the light cone, outside the light cone, and all that.
Mm-hmm.
So for me, CFT, being a field theory, describes excitations only near the Fermi points. Low
Yes.
energy excitations. Anything that's below is not described by CFT.
Yes. In fact,
That's what you're saying.
that's exactly. I agree completely. In fact, I mean, this term I didn't say, but as you see, it has nothing to do with CFT. So it's just that for I mean, in order to do the comparison with numerics, we need to take into account also that. Otherwise, it doesn't match, of course. But this is just so it's like basically what I'm saying is the following. So if you consider the fermionic propagator as a function of x at a fixed time, so CFT will give you some something like that, some excitation like that. But actually, if you see numerics, you see something like that. So there is a constant term which is given by this semi-classical argument, and on top of that, there is the CFT contribution, which in this case just gives, in fact, the next to leading term. So I just showed how to take it into account, but it has nothing to do with CFT.
Okay.
Yeah.
So this brings me to my next question. I never understood Fermi liquid theory, but I'm sure the old Russian school would say, oh, we know all this, right? Because this is Fermi liquid theory, which you're doing. You're actually not using any CFT. You're just using a Fermi particle, a Fermi picture around of excitations near the Fermi surface. So hasn't this been kind of considered in other contexts before?
Yeah, that's a very...
You must know everything about fermi-liquid theory, no?
So that's a good question.
Or when you look at Maham's book about any particular, interacting particle theory and diagrammatics and all that, I kind of think I've seen this before. But okay, so that's just a general question. Did you look up the literature on this?
Yeah, so that's a good question. So what I know is that basically, I would say that, for example, the fermionic propagator, I'm pretty sure that you can get with other methods. Probably you just, as also in LPTMS, they were telling me, probably it's already enough to look to semi-classics to get most of that, okay? And so in that case, in fact, I don't know if this is really the power of this thing. But for example, already when you consider the one particle density matrix, I didn't find many results, and mostly. But I think that the really new, what the real power of this method is that this allows you to compute entanglement entropies, and and this is not known. So this is something that, as I was saying, we are doing for this quench from the double well, because there you can you can also do in this case, but it's more trivial. In this case, you will get something quite fun actually, and so the entanglement entropies and also. This is all the framework. This is our starting point, the non-interacting case, to go towards interactions. So this is the idea of
But on this picture, the difference between
it is harmonic and harmonic potential.
X4 again.
X to the fourth.
And it changed completely.
Yeah, because you go. This is a very particular case because it's the harmonic case. In the harmonic case, in fact. In my case, for example, you would not see any thermalization, right? Because your Wigner function under an harmonic evolution just turns around. So basically, the evolution is periodic. You don't see any thermalization. Anything happens in time. You always you just need to look at a period, and that's it. Okay, that's all you need. Instead, as soon as you switch on even a little an harmonic evolution, then you start seeing something like that. And so as time passes, you see that there are more and more Fermi points. In this situation, this was something just like in the last slide you put something that, but it's not something that I'm sure we can do with this method. In particular, because after talking with people last week in Orsay, so there is this issue that as soon as the Fermi points get very close, you see that the agreements start to be worse, okay? So in this case, you know that as time passes, you basically, these start to be a continuum at the end. So I'm not sure that this method can really say something about the harmonic case, but yeah.
Okay.
Yeah, so about the metric that you have used, the background, so you consider a classical background, but
yes.
Is there any regime where you should consider the fluctuations of the metrics?
Yeah, that's a good question. I didn't think about that, to be honest. I was, there were also other people suggesting me to start looking into something like that. So if maybe at least consider some back reaction of the metric, if that. But at the moment, I don't know to what this would correspond in my macroscopic model, in a sense. Okay, so it would be interesting to start thinking about that, but I didn't up to now.
I suppose if the potential is rapidly varying.
All right, so maybe 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 that could be the regime, right? Yeah, no, that's interesting actually. Yeah, I think I will have a look at a certain point. Yeah, thanks.
Has it anything to do with this Floquet dynamics when you
make this? It has to do because it's periodic, yes. But I don't know if there is something deeper.
No, I mean, why did you consider, or experimentally, these people look at this?
Ah, yeah, that's for sure, yes. Yeah. Yes, this breathing Tonks-Girardeau gas is it's actually something that, which has been observed experimentally. I should put actually the reference. Yeah.
But even, for instance, you breathing Tonks-Girardeau gas, if you just look at this hydrodynamic equation, so it goes back not to Russian, but 100 years before to British. If you take like P equal, as you said, rho cube or something, so it's essentially equations without potential. It would be equation of the shallow water.
Of the what?
Shallow water.
Mm-hmm.
So rho would be h of this shallow water. So when waves are much longer than the width of the and so the British studied it. So and you know, when they were deriving Cartwright de Vries, that kind of things. Anyway, so but in your case, so those equations which you wrote here, so they, because there are no dissipation, so it would be, for instance, shock waves, even without any potential. If you have, I don't know, some initial profile. So is it interesting how they kind of, you know, with these shock waves, you know, which I avoided seemingly. Yeah, so your geometric, you know, this, what you said, background, you know, rather than being flat, becoming, you know, curved, something interesting can happen.
I mean, shock waves just correspond. I think that is somehow related to this question of multiple Fermi points, right? Because the shock wave in general comes exactly when you have this.
That's right, and you replace them by this Maxwell construction. That's right.
Yeah. So I mean, I still don't have an answer, let's say, for that, but it's something that we are investigating. The point is exactly this: that in this language, I mean, and also in the generalized dynamics language, you don't have basically these shock waves because I mean, in this in the phase space, if you look to phase space, everything is smooth. Okay, so basically, at least as far as I understand, these shock waves is something that you see when you look just in the space. Okay.
Right.
But if you look instead in phase space, everything is smooth. So it's not. Yeah, let's say that there's nothing special is happening there from this. In a sense, this perspective from the phase space solve this kind of divergences which are not really there in somehow. Okay. I would say like that. Yeah.